All right, this is Chapter 5 homework for Physics 201. So the shopper in a supermarket pushes a cart with a force of 35 newtons, directed at an angle of 25 degrees downward from the horizontal. Find the work done by the shopper as it moves down a 50-meter length of aisle. So here's our shopping cart. We're pushing downward with a force of 35 newtons, and the angle here, this angle right here, is 25 degrees. So our force, or excuse me, my displacement is in this direction, and my force is in this direction, and this angle is 25 degrees. Well, I know that work is equal to the force vector dotted with the displacement vector, the dot product of that. The dot product by definition is FD cosine of theta. So in this case, that's going to be the component of the force that's in the same direction as the displacement. So if I looked at that, it would be this component of the force, the x component. Right, so this is going to be F cosine theta times d. That's where that comes from. So I just put in my numbers here. I have 35 times 50 times the cosine of 25 degrees. And that gives me the answer, which is 1600 joules. All right. I have another way you could do this if you want to think about it more in terms of the definition of the dot product. This is the more difficult way to do it, but you could do it this way. You could define the force in terms of its I and j components. So that's going to be 35 cosine of 25 I minus 35 sine of 25 j. So those are just the x and y components of the force vector. D, the displacement, is just 50I. And then we just take the dot product. F dot D is going to equal 35 cosine of 25I minus 35 sine of 25j. That's my F, dotted with 50I. And then I remember that I dot I is equal to 1, and j dot j, or I dot j rather, is equal to 0. And I do FOIL on this, or I just multiply these out, getting rid of my I dot j or j dot I terms, and I just get 35 cosine of 25 times 50 times I dot I. And that gives you the same thing. It's just sort of the longer way of thinking about it, but it's 1600 joules. All right, it's just, this is the definition of F dot D, and it's a lot easier going that way. All right, outfielder throws a 0.15 kilogram baseball. That's my mass at a speed of 40 meters per second. That's my velocity, angle of 30 degrees. What is the kinetic energy of the ball at the highest point of motion? So remember back from projectile motion. At the highest point of motion, Vy is equal to 0, and Vx is going to be equal to V naught cosine of theta. So I want to figure out the energy, the kinetic energy at the highest point of motion. The kinetic energy is 1/2 mv squared. At the top, that's just going to be Vx, because Vy is going to go to 0. So it's going to be 1/2 m V naught cosine of theta squared. That's my x component of the velocity. And so that's going to put in my numbers here, 0.150 kilograms times V naught, which is 40, times cosine of 30. That whole thing is squared, And then putting in those values, I get 89.8 joules. I get Vx 40.0 cosine. Vx works out to be 34.6. Put that in here. And then we get 89.8 joules. All right. You know, this doesn't ask this, but it's a good aside, and it's a good problem that you should know how to do. But how could we use this information to find the height of the object? All right. Well, we know that the total energy doesn't change, right? And so the energy that it has here, it has only kinetic energy, and its potential energy equals 0. So its kinetic energy is something greater than 0, but its potential energy is 0. It only has kinetic energy at the bottom. And since I know its speed at the bottom, I can determine its total energy. So as I said, this is just an aside, but its total energy, which is equal to the kinetic energy at the bottom, is going to be 1/2 mv naught squared. All right, so that's 1/2, what was the mass? 0.15 times its initial velocity, which was 40 meters per second. That's pretty fast. That's like 100 miles an hour almost. That gives me its total energy at the bottom, which is 120 joules. All right. Then I know then at the top up here, I know that its kinetic energy at the top is 89.8. I'm just going to call that 90 joules to make it easier. That means that the potential energy has to be 120 minus 90, which is equal to 30 joules. All right, so I know the potential energy at the top, as I wrote it there, I'll just write it again, is 120, that's your total energy from here, minus 90 joules. That's your kinetic energy at the top. That means it has 30 joules of potential energy at the top. And then I say 30 joules is equal to m times g times h. So h is equal to 30 joules which gives me 20.4 meters. So that's the height. That's this distance, h. We're going to work problems similar to this, but it's a good one to have for now. It wasn't asked in the problem, but you should know how to work that. If I'm the height from which you would have to drop a ball, so it'd have a speed of 9 meters per second just before it hits the ground. I'm going to drop a ball a certain height. I want to know what is this height so that at the bottom, just before it hits, it has a velocity of 9 meters per second. All right, so I need to look at my energy. I know that energy is conserved, so the total amount of energy is always the same. At the top, it only has potential energy, and its kinetic energy equals 0 because it's at rest. You're dropping it from rest. The potential energy is something greater than 0. At the bottom, the potential energy equals 0, and the kinetic energy is something greater than 0. So I'm going to take the potential energy at the top plus the kinetic energy at the top equals the potential energy at the bottom plus the kinetic energy at the bottom, but then recognizing that that and that are both 0. So this is going to be mgh, that's the height that you release it from, is equal to 1/2 mv squared. That's the velocity at the bottom, or the speed at the bottom. The masses cancel is good because we don't know it anyway. And I'm solving for h is going to be v squared over 2g. That is 9 squared over 2. It's 9.8. See, that's 81 over 20. Should be about 4. Yeah, 4.1 meters. An athlete on a trampoline jumps straight up into the air with an initial speed of 9 meters per second. Find the maximum height reached by the athlete relative to the trampoline and the speed when she is halfway up to her maximum height. So here's my trampoline. I'm going up. My initial speed at the bottom equals 9 meters per second. She goes up, it comes back down again. All right, we could work this the way we did the kinematics problems a few chapters ago, second chapter, I guess, where we find the time required to go up to the top because we know the velocity goes to 0 and yada, yada, yada. But it's a lot easier to do it this way, all right? Because, sorry, I know that my potential energy down here equals 0, my kinetic energy is greater than 0, and up here, my potential energy is greater than 0, but my kinetic energy equals 0. So just like we did in the previous problem, and in fact the numbers are the same, so you can probably figure out what our height is going to be. I can take the kinetic energy at the bottom and set that equal to the potential energy at the top. The kinetic energy, the potential energy at the bottom is 0, and the kinetic energy at the top is 0, so those I don't include. All right, and then I just say 1/2 mv squared, that's v at the bottom, is equal to mgh. My masses cancel, and what am I looking for? I'm looking for h. All right, h is v squared over 2g, but the same numbers we had last time. So this young lady goes up to 4.1 meters. 4.1 meters is my height. Now, what is the speed of the athlete when she is halfway up to her maximum height? All right, so that's what that is. I want to know what is her speed here when she's halfway up. That is, what if h is equal to, let's just call it 2 meters, okay, just to make it a little easier. So this is part A. Part B, if h equals 2 meters, what is her speed? All right, so now I'm going to have the total energy. You know, the total energy you can use at the bottom or at the top. The total energy is always the same. Let's just take the potential energy at the top, which is a measure of the total energy, is equal to her energy halfway. So that's going to be potential energy half plus her kinetic energy at the halfway point. Potential energy at the top is mgh equals mgh over 2. That's going to be my 2 meters plus 1/2 mv squared. My masses all cancel, and I'm looking for the speed. So I'm going to take this term and take it over to the left-hand side, and that'll give me gh over 2 equals 1/2 v squared. I'll double both sides and take the square root. So v is equal to the root of gh. All right, now where h is my 4.1 meters. So that's the root of 9.8. It's 4.1. That's going to be 6.4 meters per second. You might get a slightly different answer depending upon how you put in the numbers, but it's going to be close to this. Like if you actually take this 2 meters and then you put that in here instead of h over 2, but it should be pretty darn close to that, 6.4. All right, a 50 kilogram pole vaulter running at 10 meters per second vaults over the bar. Her speed when she is above the bar is 1 meter per second. Neglect air resistance, energy absorbed by the pole. Determine her altitude as she crosses the bar. All right, pole vaulter. Boop, 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 boop. And she jumps, goes over the bar, and comes back down. All right, down here, she has kinetic energy greater than 0. Her potential energy equals 0. Up here, she has both kinetic energy and potential energy. Both of them are greater than 0. That's because at the top, she doesn't come. She has a speed as she's going over the bar, right? Because she's traveling on a parabolic for a projectile motion. She's has velocity in the x direction and the y direction. Her velocity in the y direction goes to 0, so the velocity in the x direction, it remains constant. It's 1 meter per second in this case. All right. So I want to determine what is this distance. H. I take the energy at the bottom, that's just going to be the kinetic energy, and I set that equal to the kinetic energy at the top plus the potential energy at the top. Now remember, I still have this potential energy at the bottom term here, but it's equal to 0, as I said right here. So that's why I didn't write it. I have 1/2 m v naught squared. I'm going to call this 10 meters per second v naught equals 1/2 mv squared. I'll call this 1 meter per second v plus mg times h. And h is what I want to know. M's cancel. I get 1/2 of v naught squared, that's half of 100, equals 1/2 of 1. See, that's 49.5 divided by 9.8. I carry all my proper sig figs, I get 5.1 meters. That's the answer. A skier of mass 70 kilograms is pulled up a slope by a motor-driven cable. How much work is required to pull him 60 meters up a 30-degree slope? Assume frictionless at a constant speed of 2 meters per second. What power must a motor have to perform this task? All right, so this situation, this is a 30-degree slope. It's not really drawn to scale. I have a skier, I'll draw him as a box. He's being pulled up that slope at a speed of 2 meters per second. I want to know what power a motor must have to perform this task, and what's the work that's being done. Now remember, work is equal to F dot D, dot product of the force and the displacement, and my force is this force. I need to figure out what is that force. If I draw my other vectors, I have a force weight here, and then I have the normal force. And if you remember back to when we were doing vector diagrams, this is my normal force. This is my force here. And then I have my weight, which is over here, and this angle is 60 degrees. I can resolve that weight into two components. This is Fw cosine of 60, and then this is Fw sine of 60. So, by looking at my x here, I can say that F equals Fw cosine of 60. All right, F is equal to Fw cosine 60. So, I can put that in here. That's my force. Fw cosine of 60, all right, times the displacement, which is 60 meters, times the cosine of the angle between the force and the displacement. Now my force is in this direction, and my displacement is also in that direction, so that cosine is 0 degrees. You have to be careful about this, that you make sure that your angles are all right, because you have this 30 degrees and you might be inclined to use that, but you really need to think more about, well, what is this angle telling me? Really, I want to know the angle between the force and the displacement. And in this case, I think it's easier just to determine the force, which is a component of the weight, and then that force is in the same direction as the displacement. All right, so now we're almost there. The weight is just 70 times 9.8 times cosine of 60 degrees times 60 meters, and then cosine of 0 is just 1, so 70 times 9.8 is 340. And that's equal to 20,000 joules. All right. We also need to know what is the power, part B. Power is defined as work over time. So we could ask ourselves, well, how long does it take to go 60 meters at 2 meters per second? All right, and you would come up with, well, 60 divided by 2 is 30 seconds. All right, so we could just take that 20,000 joules divided by 30 seconds, and we would get 680. 680 watts. Let me just double check that number. 20,000 over 30 seconds. Okay, you actually get 670. But let me show you another way to do this. All right, 680, it sort of depends how you round. Another way to do this, because the actual definition of power is F dot V. The dot product of the force and the velocity. The force, as we've already said, is 340 newtons. And remember, this is the definition is FV cosine of theta. So we have 340 newtons, 2 meters per second, times the cosine of the angle, which remember the cosine between the force and the displacement is 0 degrees. Cosine of 0 is 1. 680 watts. 1 watt is equal to 1 joule per second. All right, so that's power. That's the definition of power. In this figure, a bead of mass of 100 grams on a track and initially at rest at a height of 1 meter. The blue portion of the track is frictionless. What is the speed of the bead at the first hill, h2? And then assuming the orange portion of the track is frictionless, to what height does the bead rise before stopping on the right-hand side? And then we're going to consider the right-hand portion of the track to be not frictionless, but to have a frictional force of 0.2 newtons. What height does the bead reach on the right-hand side before coming to rest? All right. First part of this is pretty simple. And then the second part gets a little complicated. I have this distance is 1 meter. The mass is 100 grams, so this is 0.1 kilograms. And I want to know the speed right here. This, of course, if h is 1 meter, this is 0.5 meters. All right, so for part A, and let's see, it was at rest initially, right? It was at rest. So right here, it only has potential energy. The kinetic energy equals 0. Here, it has potential energy and kinetic energy. Has potential energy and kinetic energy. Now, if I say that the energy up here is equal to the energy down here, which is just a statement of the conservation of energy, I'll say that the potential energy at the top, or at h, is equal to the potential energy plus the kinetic energy that's at this location, at h over 2. All right, so I get m times g times h equals m times g times h over 2 plus 1/2 mv squared. My m's cancel. I want to solve for v, so I'm going to take this over here. I get gh minus gh over 2, which is going to be gh over 2. I'm going to double this and square root it to get my answer for v. Those 2's cancel. So it's just going to be the square root of gh, the square root of 9.8 times 1, and the square root of 9.8 is 3.1 meters per second. All right, so that's my answer for that part. Now, the second part, part B, I wanted to know what is the height that it attains over on this side. Now, the quick answer to this, if there's no friction, is that the height is 1 meter. All right, let me show you how that works out. Because over here, I only have potential energy, And over here, I'm only going to have potential energy as well. So the potential energy is going to equal the potential energy. So mgh is going to equal mgh. We'll call this h on the left and this h on the right, but it doesn't matter because these things cancel. And so hl is equal to hr. So that means that this distance is also going to be 1 meter. But you shouldn't have to calculate that. You should just be able to look at it and say, well, since there's no frictional forces, then the ball comes up to exactly the same position where it left, since there's no friction acting. All right, now for part C of this, number 7. Now consider the right-hand portion of the track, shown here in orange, is not frictionless. The force due to kinetic friction is 0.2 newtons. And I want to know how high does the bead reach on the right-hand side before coming to rest. All right, so first I'm going to consider the potential energy over here. Remember, the potential energy over here, that's equal to the total energy because the kinetic energy is equal to 0. And then this bead is going to come some distance up here. It's not going to come back to the original distance, but it's going to come some distance up. Now, I can set the amount of energy on the left-hand side, which is the potential energy. I'll call this potential energy left. It has to equal the potential energy on the right plus the work that is done by friction. All right? So plus the work that's done by friction. Now I can put in some values here. I know this is mg times h, and then this is going to equal mg times I need to let me draw some pictures here. So let's say that I have it go up to this height right here. So it comes up to this point and stops. I'm going to call this h prime. Okay, so that'll be h prime plus 0.5 meters. All right, so this distance right here from here to here is 0.5 meters. I know that because this is h over 2, which is a half a meter. All right, so that's the potential energy when it reaches that point, plus the kinetic friction times the distance that it travels. And this distance is going to be that distance d. That's why I define this h prime, the height, in terms of h prime, because I'm going to need to list it in terms of d. All right, now I can say that the sine of 30 degrees equals what is it? Opposite over hypotenuse. That's going to be h prime over d. So then I can say that d is equal to h prime over sine 30. All right, I'm going to take this and substitute it in for d, and then that's going to give me an expression with only h prime. Let's go ahead and put in some numbers here. I'm going to take this and make the substitutions over here, putting in some numbers as well. I have 0.1 kilograms times 9.8 times my height, which is 1 meter, and then that's equal to 0.1 times 9.8 times h prime plus 0.5 plus 0.2. That's my kinetic frictional force times h prime over sine of 30. All right, let's take some of these and combine them. This 0.1 times 9.8 times 1 is just going to be 1. It's actually 0.98, but rounding off to 1 equals 0.1 times 9.8, again, is 1 times h prime plus 5, plus 0.5 rather, plus 0.2 over sine of 30. It's going to be 0.2 over 0.5 h prime. That should be a 0.4 h prime. And then I solve for h prime. if I get h prime, I find that h prime is equal to 0.36 meters. All right, that tells me that this distance is 0.36 meters, but I really want to know what is that distance. All right, and so that distance, I'll call it HR for h on the right side. So HR is going to equal to 0.5 plus 0.36, which would be 0.9 meters. So whereas it started at 1 meter, it ends at 90 centimeters, 10 centimeters below where it started, because the work done by friction takes away some of the energy. All right. There's another page. All right, this figure shows a mass of 1 kilogram on a spring with a spring constant of 550 newtons per meter. So K is equal to 550 newtons per meter. Immediately to the right of the equilibrium position, there is a region where a frictional force is present. That's right here. You have a frictional force present. The force is dependent upon the position is given below. The region extends 4 centimeters to the right of the equilibrium position. So this gives the magnitude of the force, and because it's a frictional force, we'll say that it always opposes the motion. So if the motion is positive, that's going to be negative, all right? Because it's frictional force, so it always has to oppose the motion. Now, I want to know what is the initial total energy of the system. All right, that's fairly simple. For part A, I just say the initial potential energy of the spring. That is the potential energy right here, because I know that right here its velocity is 0, so it only has potential energy. This is elastic potential energy, so it's 1/2 kx squared. That's going to be 1/2 times 550 newtons per meter times x. This is x equal to 10 centimeters, or 0.10 meters squared. And that gives me an energy of 2.8 joules. That's my total energy. After release, what is the speed of the block at 5 centimeters to the left of the equilibrium position? So I want to know what is the speed right here. All right, so for part B, I know that the total energy is 2.8 joules. And so that's going to equal to the potential energy at 5 centimeters plus the kinetic energy at 5 centimeters. That is 2.8 equals 1/2 k times x squared plus 1/2 mv squared. I'll go ahead and put in some numbers here. I'll carry it down here. Get 2.8 equals 225. That's half of, let's see, what was k? K was 5, yeah, half of 550, which is 225, times x, that's going to be 0.05 meters squared, plus 1/2 of the mass, which is 1 kilogram, times the velocity squared. All right, if I solve that for the velocity, let's see, I get 2.8 minus 225 times 0.05 squared divided by 1/2 times 1, and then I square root it. I get 2.1 meters per second. 2.1 meters per second. So that's part B. How much energy is lost each time the block goes through the region with friction? Let's do that up here. I'll do part C right here. I want to know how much energy is lost. So I think I have this on the next page. Yeah, we'll just do it down here. So for part C, the work done by this force, which is dependent upon position, is equal to the force dx. All right. So to find the total work, I'm going to integrate. So the work is equal to the integral of f dx. F is 5,000 x squared dx. And I'm integrating from 0 to 0.04 meters, because that is the length over which this force acts, to 4 centimeters. And so that gives me 5,000 x cubed over 3. I'm going to integrate from 0 to 0.04, and I will find the amount of energy doing the limits of that integration is 0.107 joules. All right. Now, in part D, I want to know how many times it's gonna go back and forth. Each time it goes across this little patch of friction, it loses this amount of energy, 0.107 joules. So to find the total number of times is fairly simple. I know that the total energy, as we found before, equals 2.8 joules. So I just want to know how many times it's going to go until it loses all of that energy. So I just say 2.8 divided by 0.107, and that's equal to 26.2. Right? That means that it's going to go through 26 times, and then on the 27th time it's going to stop. So I'm just going to say that it goes through 26 times. It has a little bit of energy left over after going 26 times, and then in that 27th time when it goes through that little patch of friction, that's when it's going to stop. All right, one more. Force acts on a particle which is initially at rest. There's a force in vector notation. Its initial position. After so much time, the particle is at a new position. How much work has been done by the force? All right, well, I know that work is the dot product of F and D. So I need to write out my force and my displacement in vector notation. Work equals the dot product of F dot D. That is 3I plus 4J. Dotted with my displacement vector. My displacement vector is going to equal to dF minus dI, which is going to be 3.25 minus 0.25, so that's 3I, 4.5 minus 0.5, minus 4J. Or excuse me, plus 4J. All right, 4.5 minus 0.5. All right, so that's going to be 3I plus 4J. I'm going to have 9 I dot I plus 16 J dot J. All right, remember I dot I equals 1, J dot J also equals 1. I have other terms, I'll write them here, but you don't normally write them. It's going to be 12 J dot I. And let's see, 3 times 4, 12 I dot J. All right, but these both equal 0, so both of those are going to go away. So I wind up with just 9 plus 16, which is equal to 25 joules. So there's been 25 joules of work done by the force. In part B, I want to know what is the power equal to. Can do this pretty simply. Power is just defined as work over time, which is going to be 25 joules over 2 seconds, which is equal to 13 watts. Part C, what is the mass of the particle? All right, in order to find this, I'm going to find the acceleration of the particle. And then, given the force, I'll find the mass. All right, so I can find the acceleration. Let's see, I have initial and final positions, and I have a time for both of these. I'm going to break this up into its x and y components. Oh, I also know that v naught is equal to 0. V naught x equals 0, and v naught y equals 0. All right, first I'm going to say that x equals 1/2 ax t squared. and then I'll say, actually, I'm going to have to leave on, let me come back here, erase this. X equals x naught plus 1/2. Let me just write it all out, just to be clear. Plus v naught t plus 1/2 at squared. Now here, v naught x, we've already said is 0. I can say x minus x naught equals 1/2 ax t squared. Now here I know x and x naught. That was, if you go back up, that's 3.25 minus 0.25 equals 1/2 ax, and then t was 2 seconds. 2 seconds squared. If I solve for ax is equal to 3/2 meters per second squared. All right, now I also want to find what is the y acceleration, so I'm going to do a similar thing. Y equals y naught plus v naught y t plus 1/2 ay t squared. This goes to 0 just like it did before. I get 4.5 minus 0.5, that's my initial and final positions, equals to 1/2 ay 2 seconds squared. And then I find ay is equal to 4 over 2, which is equal to 2 meters per second squared. All right, so now I can write my acceleration in vector form is 3/2 I plus 2j. I know that my force is equal to 3I plus 4j. So I can say F equals ma and find my mass. So I get 3I plus 4j equals the mass times 3/2 I plus 2j. And you can consider either the x or the y components in order to find m. So actually on this side you would either have to do either the x or either the y. Alright, so I can say that 3I has to equal m times 3/2 I. And then I can also say that 4j has to equal m times 2j. Because I know that the x and y components of the forces have to obey by Newton's law. That is to say, let me write this out, that Fx equals m times ax, or Fy equals m times ay. Either way, in both cases, I find that mass is equal to 2 kilograms. All right, I think that was the last thing on that. Oh, what is the magnitude of the final velocity for the particle? Well, now I know its acceleration. So to find the magnitude of the final velocity, I just say v equals v naught plus at. V naught is 0. I'm going to find vx. Vx is going to equal to ax times t. And then similarly, vy will equal to ay times t. Ax is up here, 3/2 times 2 seconds. So that's 3 meters per second. Vy is going to be 2 meters per second squared times 2 seconds. So that's 4 meters per second. So I have 3 and 4. So the magnitude of my velocity at that point is going to be 3 squared plus 4 squared. Of course, that's 5 meters per second.